All right, so let's do an example of a chi-squared goodness of fit test. This example is called Birthdays in Hockey. In his book Outliers, Malcolm Gladwell, some of you guys may have even read or heard of this book. It's pretty popular. He suggests that hockey players' birth month has a big influence on their chance to make it at the highest levels of the game. Specifically, because January 1 is the cutoff date for youth leagues in Canada, where many NHL players are from, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, more coordinated, hence they get more playing time, more coaching. If they play more, if they get more confidence, then they're going to get better, and if they get better, then they're going to, kind of this cycle of being more successful. To see if birth month is related to success, judged by whether they make it into NHL, a random sample of 80 Canadian hockey players from a recent season was selected, and their birthday quarter was recorded. So we got 80 total players here, and 32 were born in the months of January to March, 20, 16, and 12. So this gives us some evidence to support his hypothesis, because he's saying that there should be more here and less here because these guys are going to be the youngest. So, and even there's even kind of a progression there. So the question though is, do these provide convincing evidence that the birthdays of all NHL players are not uniformly distributed throughout the year? Maybe they are uniformly distributed through the year, and then this kind of variability just came up because of our sampling. You take a sample one time, maybe you get 32, 20, 16, 12. Take a sample another time, maybe this is 32, and this is 20, and this is 16, and this is 12. So is this evidence that significantly different? Is this evidence of a significant difference in the population? Let's run a goodness of fit test. P-step, we always skip the P-step or I always skip this P-step in a chi-squared test. So I'm going to go right to the hypotheses. No. The true distribution? No. The birth months of all Canadian NHL players is equally distributed throughout the year. All birth months are equally distributed throughout the year. Versus the alternate, that the birth months of NHL players are not equally distributed throughout the year. Okay? So I'm hoping to find evidence that they are not equally distributed. I want this to be significant. If I don't have enough evidence, though, I'm going to say, you know what? I can't conclude the so who knows, right? Phantoms, A, check the conditions. 1, the sample was randomly selected, I think, right? They randomly selected 20, so the sample was randomly selected. Two, N equals 80 is that less than 10% of all hockey players, all Canadian hockey players in the NHL? 32 teams, 20 players per team, maybe 25 players per team. So if there's 25 players per team, we're at 80 players. 80 is exactly 10%. If there's less, we're less than. And actually, we're less than anyway, because even if there were 800 NHL players, I think only about 2/3 of them are Canadian. So this fails. Is not less than 10% of all. So that is a concern. So that's a concern. So we should maybe make a note at the end to say, but we might have some problems here. The thing is, this is a problem that actually was working in our favor. If we run this test at an alpha level of 5%, If we fail the 10% condition, we're not going to make a type 1 error 5% of the time. We're actually going to make it less than 5% of the time. So that's actually not an error that hurts us. So I'm going to run it anyway. Large counts. Here we have to find out if the expected counts, if all expected counts are greater than or equal to 5. So I have to calculate the expected counts. Well, I'm assuming that I'm hypothesizing that they're equally distributed. If they're equally distributed and there's 80 players, then we would put 20 in each cell across. Basically, we're going to take that 80 and divide by 4. So this does check out. I could say, see the table. Remember on your test, you need to have your expected counts somewhere on your paper. This is good enough. That's actually kind of a fairly well-known procedure, is to put it in parentheses next to the observed counts. Or you could list them. You could say expected counts, and just kind of list them, 20, 20, 20, 20. Okay? So, conditions check. Name the test. Chi-square goodness of fit test. Degrees of freedom equals, there's 4 responses. 4 minus 1 is 3 degrees of freedom. Test statistic. Obtain a p-value. Make your statistical decision. We could do this by hand, but I do want to show you how to do the calculator. By the way, to do it by hand, I would calculate the observed minus expected squared over the expected, plus, do that for every single cell. It would be very easy to do by hand. As long as we name the test, though, we don't have to show our work. We don't have to show the formula. We can just use our calculator. So let's just use our calculator. In order to do this on the calculator, we need to have our data into a list. Both our observed counts, we'll call them OOO, and our expected counts, let's call it EEE. So this was 32, 20, 16, 12, and our expected counts were 20, 20, 20, 20. So make sure your observed and expected are in a list. Then from your home page, we go to Menu, Statistics, Stat Tests, because this is a hypothesis test, Goodness of Fit, Observed List, OOO, Expected List, EEE. Now it is kind of interesting that you have to put the degrees of freedom in there, and there's a reason for that. I think some other Goodness of Fit tests might not be number of responses minus 1, maybe. I really don't know. But we're 3, so we do have to put in the right degrees of freedom. Everything will be wrong if we don't put in the right degrees of freedom. It calculates our chi-squared test statistic, our p-value. It repeats our degrees of freedom. Then it has this comp list, which we may want to talk about here in a bit. So 11.2 and 0.0107. Chi-squared is 11.2, and the p-value is 0.0107. Make your statistical conclusion. The p-val is 0.0107 is less than 0.05, which is our traditional alpha value. So we reject the null. So let's make our statistical conclusion. We do have convincing evidence that and what are we going to say here? Remember, we always word it in terms of the ha. Now with chi-squared, our ha is actually a sentence, so we can literally just copy that sentence down. That the, what was it again? The birth months, that the birth months of all Canadian NHL players is not equally distributed throughout the year. So that means there's a difference somewhere. Where's that difference? Well, I guess we could look at it and say, well, it looks like that difference is here and here. Those two look different. Do these data provide convincing evidence that being born in January to March causes an increase in the probability? No. This was not an experiment. Treatments were not randomly assigned. Therefore, can't prove causation. Maybe it's something else. Maybe, I don't know, maybe there's some other reason that people are born in January. I mean, who knows, right? That is a chi-squared goodness of fit. I mean, it's just another hypothesis test. A lot of things are the same. There's just a few things that you got to change, different calculator function, but it's about the same.